similar. And now, okay, so all of us are known the Drell-Yan, okay, the Drell-Yan process, because this is most intensively studied process in QCD. And the data of the Drell-Yan process has been used to extract various non-particle inputs, like a parton distribution function, transverse momentum dependent parton distribution, either polarized or polarized. So then we use the data of this process to determine these non-particle inputs. It means that we have understood this process quite clearly. But in fact, this is not the case, okay? Because an anomaly still exists since 80s. And so in the Lanton relation, okay, this relation is supposed to be obeyed by lepton angular distributions produced in Drell-Yan process. In fact, I'll show you that this relation violated in pion-induced Drell-Yan process. So, okay, let's explain what's the violation of Lanton relation. Okay, this is the diagram for the Drell-Yan process. You collide two hadrons, so the quark and that quark annihilate into a shear photon, and then produce the lepton pair, L and L bar. If we can study this process in so-called Collins super frame. This frame is defined as the central mass frame of the lepton pair. Okay, so you can see that the lepton and the anti-lepton, okay, is located on this y plane. We use the dashed line, means that this L prime momentum is behind this green plane. Okay, so this L and L prime are located on this y plane. Then because in general this lepton pair can carry transverse momentum, so we have to boost, okay, this Collins super frame. So once we do this boost, then the beam momentum will point downward, or possibly, okay, downward. So you can see that these two beams will momentum will look like this. Okay, they may move downward. So, and also because the transverse momentum can have arbitrary angle phi. Okay, this transverse momentum can produce this way or the other way. So so the phi is arbitrary. So then we can draw this green plane to contain this beam momentum, P1 and P2, and these two planes can separated by this angle phi, arbitrary angle phi. Okay, so then we define this z-axis such that the angle here, okay, of these two beam momenta have the same angle. These two angles are equal. We define this so-called the z-axis. Then the lepton and the z, okay, is separated by the angle theta. Okay, so this is the angular. Okay, once we define theta and phi, we can define the angular distribution of the lepton pair. So in general, you can decompose the angular distribution in 4 terms. The first term is independent of angular coordinates. The second term is the well-known cosine theta squared. Okay. So if you do the calculation in the cross section of the lepton pair production, okay, from an offshore photon, you will get 1 plus cosine theta squared. I think if you have taken the course of particle physics, you should know this formula. And if we consider that the general case is finite lepton transverse momentum, then we can have the phi dependence. So the cosine phi, cosine 2 phi here. So in general, we have 4 terms. And let's call the coefficient as 1, lambda, mu, and nu. Okay. Then at the zeroth order, we have known that we have the famous formula 1 plus cosine theta squared. So lambda equal to 1, mu and nu equal to 0. Or we can go to that. You can check. You can calculate the coefficient to high orders, and we have shown that this coefficient satisfy the Lanton relation. Okay, we published in 1978 that 1 minus lambda minus 2 nu equal to 0. And Jianwei Chu, okay, told me that in fact they have proved this relation to all orders. So they performed the resummation of the large logarithm to orders, and Jianwei Chu can show that the resummation result still satisfies this Lanton relation. So it means this Lanton relation holds, okay, solidly. So then we can compare this Lanton relation with the data. So we have people have performed the data, the PP collision, PD collision, and you can see that this is a lambda, okay, it's about constant, 1. Nu is small, nu also small, and the certain deviation is small, okay, because lambda are close to 1, so 1 minus lambda is small, nu is small. So you can see it's basically consistent with data on the PP and PD. Now, you look at the plot on the left-hand side, you can see some deviation. And this deviation comes from the pion-induced Drell-Yan process. You can collect the pion on the tungsten, and so you can see the data show some deviation. Okay, okay, nu become larger when the QT or PD is larger. So the deviation, okay, increase with the lepton pair transverse momentum.
Can you give an intuitive feeling of the Latin relation?
Later.
Okay.
Yeah, later. So this I collect the pion-induced data in this plot. So for different central mass energy, okay, you can see that lambda is about 1, mu about 0, and the nu indeed will be more obviously you can see nu increase with PT. And this dashed line means the fixed order PQC calculation. So you see the fixed, so you can see that the product correction is quite small. Okay, and this slide was prepared by Perrenjian. So from this slide, you can easily see that there's a strong deviation. You can see that this deviation could reach minus 0.5. Okay. So now why there is a Latin relation holds in the PP, PD, but violated in pion-induced Drell-Yan process? This is quite strange. So the people have a single of the possible reason. And the first one to check is the calculate the perturbative correction. And you can, as I said before, the perturbative correction in fact quite small. So you can see that the leading order, next leading order calculation, the deviation just increased up to 0.02. And remember that the deviation could be 0.5. So there's no way to use the perturbative correction to explain this deviation. That's impossible. Okay. Then how can we understand this puzzle? First, we have to answer Weizu's question. Let's have an intuitive picture for the Latin relation. Okay, you can mention it in this way. So you have the quark and that quark collide because it is a vector current. So in a naive way, we have the left-handed annihilate, and this. You should say this early. Sorry. Okay. Okay. So this diagram is the diagram for cross section. So you can see the straight line here. It means that this is amplitude. This is the complex conjugate of amplitude. So you put these two amplitudes together, you get amplitude squared. So this means cross section. So in a naive picture, we know we have a left-handed and a left-handed quark, and that quark collide, okay, annihilate. So then because if the cross section is a square of the amplitude, so we have left-handed, or right-handed. Okay, this is the most this is the naive picture for the lepton pair production in the Drell-Yan process. So once we have the left-handed, you can see, then we can have the transversely polarized photon. Because you have left-handed, so you can have photon spin 1. Or spin is a spin -1 or spin +1. Okay, left-handed or right-handed. So this is called a transversely polarized photon. Then you can imagine, then this photon will fragment, split into the lepton pair. So then this lepton intend to keep the spin of the photon. So that's the reason why when theta equal to 0, it means the theta equal to 0 means that this lepton has the spin the same as the photon spin. Okay, in this way, the probability is largest. So this is the reason why we have a 1 plus cosine theta squared. So when theta equal to 0, you have the largest probability. Okay, because the lepton intend to have the same spin, carry the spin of the photon. So if we have a transversely polarized photon, then we have the Latin relation. Then, if we want to break Langton relation, how can we do it? Then we can couple the left-handed and the right-handed quarks in this way. It means that this quark is transversely polarized. Okay, because the transverse polarized quark can be written as a linear combination of the right-handed and the left-handed, right? So only the quark is transverse polarized. Then we can have this kind of diagram for cross-section. The left and the right will appear in the same diagram, in this diagram. So left will couple to the right-handed. This diagram can occur only when the quark is polarized transversely. Okay. Then why the Langton relation will be broken if we have transversely polarized quark? It's because the parton transverse degree freedom come into play. Then the sign term will appear. Because you see, once you have a transverse degree freedom, then the lepton moves in this way. Originally you have only cosine theta, but now you can have sine theta now. So the sine term will appear. Then you know the Langton relation has no sine term. So it means that if you have the transverse polarized quark, then you can break Langton relation. Yeah. Okay. Now the next question is, how can we have transverse polarized quark? There are two ways. Okay. The first one, okay, is so-called QCD vacuum effect. Okay, this means that maybe Kervey can comment on this resolution. Okay, that means we have a non-trivial QCD vacuum. So sometimes in this region, it happens that we have a strong magnetic magnetic field. Then this quark will come into this region and annihilate. Then before they annihilate, then this magnetic field will orientate, okay, will rotate the quark speed. So for example, this quark will be anti-parallel to the magnetic field, and this anti-quark will be parallel to the magnetic field. Then in this way, we can have the transverse component of the spin. Okay. So then we can generate the transverse polarized quark through the QCD vacuum effect. So they wrote this formula. They say means this term, okay, represented the situation that these two quarks carry transverse polarization. Yeah. So for example, you have H11, H22. Okay. Then indeed they can show that once we have H11, H22, the transverse polarized quark, then the Langton relation is not equal to 0. Okay, so this Langton relation equal to the transverse, the coefficient, okay, of this transverse spin correlation. Yeah.
Excuse me. Does it have to be the vacuum, even predictively?
Next page.
Well, the vacuum effect should not go to high PT, right?
I agree. Yeah. But anyway, because the data also only appear in the low PT, in a few GeV, there's up to 3 or 4 GeV. So, not next page. Okay. the one after next. So certainly they didn't do any calculation because we don't know how to calculate QCD vacuum effect. It's a non-perturbative. So then they just argue, okay, maybe this effect is important. Then we can have the transverse polarized quark. Then they just parameterize, okay, this contribution into this form with with free parameters like a kappa 0 and also MT. Then they found that if they choose the kappa 0 equal to 0.17 and the MT about 1.5 GeV, they can explain data. So you can see that the lambda is about 1 nu. Okay, this nu. Okay, it's a nu. So nu become large, increase with KT. So this increase, in fact, comes from this penetration. You can see that this effect increase with QT. Then Kervey mentioned that whether this correlation comes only from the non-particular effect. In fact, they can have other sources or mechanisms to produce this transverse polarized spin. For example, the Bohr-Models function. Okay, they argue that because the point is that we must have a transverse spin. How to have a transverse spin? Another possibility is that if this quark spin can correlate with the quark transverse momentum, then we can have the transverse spin. Right? If these two quantities has the correlation, so they define the so-called Bohr model function, which is proportional to this KT slash. Then this KT slash will give us the transverse speed. And the effect of this correlation, the magnitude of this correlation is parameterized by the so-called Bohr model function. It's defined as H1 per. Yeah. So this H1 per just described by the strength of this correlation. And certainly, next step is that they also parameterize this Bohr model function. Okay. Then they can calculate the nu in this way, and they found that also in this region, the nu also increased with the PT or QT. But they argue that when PT is larger enough, nu will become smaller. So they argue that if we have data in the high PD region, this curve will become like this.
I have two questions here. One thing is, why is the data so limited in the QT or PT? Secondly, what does this have to do with pions?
Later.
Always later, I know.
But, for the data, that's because they do their energy is not very high, because the center mass is 190 GeV, and they do the fixed target experiment. So this reason the QT is lower. But why this has anything to do with the pion? I will explain, because this is the central issue of this talk. Yeah. Okay, now some remarks. Maybe this will answer Wei Su's question partially. Okay, first that the vacuum effect is forever blind. So how to differentiate the pion proton and the proton dy? So, right, because we just care the quark and anti-quark, and the vacuum effect will polarize this quark and anti-quark spin. It doesn't matter this quark comes from the pion or from proton. So obviously the vacuum effect is not favored. Not so good, because it's forever blind. You cannot differentiate pion proton or proton Drell-Yan. But the Bohr model, their proposal can differentiate the pion and the proton, because they can argue that it's because the anti-quark is a valence quark in a pion, but this anti-quark is a C quark in a proton. So if the C quark and the valence quark have different Bohr model functions, then it's possible to differentiate the pion and the proton.
But then for PP bar Drell-Yan, you should
That's
be
a
like
final
a
page. I know. So you see, as long as you follow the logics, you immediately come to this conclusion. Wait.
I'm sorry, I didn't get the second point.
Oh, this means that because the annihilation must occur between the quark and anti-quark. So you can ask whether it's a quark, anti-quark is a valence proton or C proton. And in a pion, so pion contains an anti-quark. So this anti-quark is a C, is the valence proton in a pion. So then you can argue that, maybe the valence quark has a larger Bohr model function, and the C quark is a smaller Bohr model function. So this is the reason why the PP bar, the PP, is a smaller violation, because the PP involves the C quark. Because you need an anti-quark. The anti-quark is the C quark in the proton. So this C quark is a smaller Bohr model function. So they can explain we don't see the violation in the PP, but we can see violation in pion proton. Yeah. So as long as you understood this logic, immediately you come to this proposal. That's major PP bar. This is the final page. Now, in fact, we was attracted by this proposal not because of the vacuum, not because we hate the vacuum effect or we dislike the Bohr model function. In fact, we was attracted to this subject because of the B-meson decay. Yeah. When I studied B-meson decay, D-meson decay, then I was attracted to this anomaly in the pion-induced Drell-Yan. So I want to tell you how we come to our resolution. So I want to show more relevant observations. So when you collect all these observations, you will see why we come to our conclusion. Let's see. The first one, the theoretical side, we need a KT factorization. The reason is simple. we know that these are two factorization theorems in the PQCD. One is a collinear, another is a KT factorization. Both are fundamental tools. Okay, but in some cases we do need a KT factorization, and the collinear factorization does not work. That's in the region of a small x. Okay, in the high energy region, or in when we study the final state spectrum, a low QT, because in these two regions, the small x means the smaller attitudinal moment fraction. Okay, so you have x times b plus, which is small, when x down to the 10 to minus 6, 10 to minus 5. Then this scale, okay, longitudinal momentum is not large compared to KT. So we have to keep a KT. Similarly, in a low QT region, for example, we study the low QT, the compare, then the QT is about same order as KT. Then we cannot neglect the KT. So once we keep a KT, we have to apply the KT factorization. Okay, so that's the reason I say here, KT factorization is appropriate for studying low QT spectrum in the Drell-Yan process. So first, we need a KT factorization to study this low QT lepton pair. Second, okay, KT factorization is valid in the complex QC process. You can see this is I used this example, okay, considered by Collins. Collins argued that okay, the KT factorization holds for simple process like a DIS. This is a simple process, so KT factorization works, no problem. But breaks down for complicated ones like this one, hadron production. So you have you collide the two hadron, produce another two hadron plus anything else. Okay, so the diagram look like this. You have initial P1, P2, they collide, exchange the hard gluon or hard photon, and they form another two final state mesons, hadrons, K3 and K4. So Collins demonstrated that KT factorization breaks down in this process. Okay, okay, to prove the KT factorization, you need to factorize this TMD, the transverse moment dependent discrete function, out of this scattering process. So for example, we want to factorize the TMD for the P1. So you can see that this pattern represented this pattern. Okay, this pattern on the right hand side represented by this pattern line here. Then this is the Wilson line. Wilson line is described by this iconopropagator. This is N is the Wilson line direction. Okay, and so so the question is whether we can factorize this TMD out of this scattering process. And so in order to
what's the relation between the two Feynman diagrams?
Oh, this is the whole scattering process.
Right.
And to prove the KT factorization, we need to factorize out this TMD for the pattern for hadron 1.
Mm-hmm.
So this is a definition of TMD. You have the incoming pattern before final state, after final state, and these two patterns because located on different space-time. So we need a Wilson link to connect these two quark fields. Then we can have a gauge invariant definition, TMD definition. Yeah. So this is the goal. This is the goal. We want to factorize this out. If we can do it, then we can prove the KT factorization. Okay. So certainly, because I mentioned the KT factorization violate, so it means that this cannot be done. Okay. So the Collins just show why, because they checked the one loop, and they found that okay, this diagram is very trivial to see that this diagram contributed to the TMD, because you just iconolize this pattern line to get a Wilson line, then you already have the definition of TMD. Then this collinear gluon couples the hadron 1 and hadron 4. This collinear gluon couples hadron 1 and hadron 2. So it means they couple the different pieces in the scattering process. So it's better that these two diagrams cancel. So then the Collins checked that okay, if we iconolize this pattern line here, we get these two iconopropagators. The first term comes from this diagram. The second term comes from this diagram because it's K4 minus L, so you get a minus sign. Then they add them together. You can see in most region of L plus they cancel, but only when L plus equal to 0, the imaginary part will add together to get a minus I data function. This if you know the principal value of prescription, you know that the sum of these two iconopropagators give this imaginary piece. But should we worry about this imaginary piece? The answer is no. because this is a cross section. Cross section must be real. So we know that this imaginary piece will be cancelled by some other diagram. For example, if collinear Coulomb change on the right-hand side of the final state, then we'll generate plus I. So this plus I will cancel this minus I. So we don't worry, okay, the KT factorization, at least at one loop level. But then Collins showed that if in two loop, you have one I here, another I, you multiply this I together, you get a real part. So now the data function, you will have the real piece, real contribution from the product of the data function. So then the Collins just say that, okay, and you calculate this set diagram, okay, with one collinear Coulomb before the final state count, another after. Then the set of this set of diagram contains two collinear Coulombs, one side of the final state count. And unfortunately, they don't cancel. They don't cancel. So that means indeed there's a coupling between the different pieces of this scaling process. It means that you do have some infrared Coulomb which again can couple the hadron 1 and hadron 2, for example. Okay, this is an infrared Coulomb called the Glauber Coulomb.
I'm sorry, what did you say about the one loop data function? Does it matter?
And you see, you can write this according to principal value prescription. You have P over L plus minus I, because it's plus I epsilon.
You
minus
just
I.
throw away the data function.
Throw away? No.
You can principal value only.
No, you have the minus I data function, so you got twice.
That's right.
Twice.
So
But
does it matter to have this?
It does not matter here, because cross section must be real. So this imaginary part will be cancelled.
I see.
Must be cancelled.
By what?
By what? For example, you have another diagram here,
Okay.
collinear Coulomb on the right hand side. So you take a complex conjugate to get plus I, so to cancel this term. Yeah, but the cancellation does not occur in a two loop layer, because now the two data function can multiply together, you get a real contribution now. And unfortunately, there's no cancellation between these two sets of diagram. Yeah. So we have this information. We need a KT factorization, but unfortunately, KT factorization will fail for complicated QC process. And this electron pair production in the Drell-Yan process is indeed a complex QC process, because you can compare the diagrams for these two processes. The left-hand side is a hadron production considered by Collins. Okay, we have shown this before. This is the Feynman diagram for the electron pair production in Drell-Yan with finite QT. Because it's finite QT, so you need some Coulomb radiation to balance the transverse momentum of the electron pair. So for finite QT, you must have this Coulomb radiation here. So you just compare these two diagrams. Very similar, right? So you have the initial state hadron, you have this final state parton here, and you have the initial parton here. So they look very similar. And so I just draw a collinear Coulomb change between the hadron 1. Then I can draw a collinear Coulomb here, just like I draw a collinear Coulomb here. So indeed, this Glauber Coulomb will break the Drell-Yan process, the factorization of Drell-Yan process. So KT factorization broken by Glauber Coulombs in process involving at least 3 hadrons. So means we have at least initial state hadron 1, and another hadron, coming hadron 2, and 1 hadron in the final state. This is a necessary condition to have this factorization violating effect by the Glauber Coulombs. So then we can draw collinear Coulomb, the Glauber Coulomb here, and then this Glauber Coulomb will break the KT factorization. So the KT factorization for Drell-Yan is broken. Okay, this is a second piece of the information. Next one, what's the effect of this factorization breaking effect? Okay, I show you. It will give a strong phase. So the idea is that you just factorize this Glauber Coulomb. In principle, okay, you can do it especially in the low QT region. Okay, but this how to do it, how to prove this is the detail I don't want to show. So I just argue like that. In a low QT region, we can factorize this Glauber Coulomb, okay, into another non-perturbed